Hello, everyone. Welcome to the April DVC meetup. So I'm Jenny, the community manager here at DVC. You see DV's with us today too? I see another DV. Excellent. Let me admit.
Yeah,
Here.
there is another DV right there.
Cool. And Vera too, right? Okay, awesome. So as you can see on this slide here, this is our distributed team. We're all around the world, just like all of our friends in the DVC community.
Hello, everyone. First of all, thank you for joining the meetup. For us, for DVC, our community and feedback community was always a major driver for new features and for new directions for DVC and for other projects. Very happy to see you here. Today, we will be talking about two topics. One is pipelines, and second one is CML, CI/CD for machine learning. Pipeline was always a big part of DVC. From DVC 1.0, we had pipelines. In the 1.0 version, like about a year ago, we introduced single DVC file when pipeline can be presented in like one single place and can be observed. It was a big step to improve this experience, and Saugat was driving this project. In DVC 2.0, we introduced new features for in the pipelines, parameters, using hyperparameters for config files, as well as loops in the pipelines. All of those are based on the community feedback. And that's what Saugat is going to talk about today. And the second talk, CI/CD for machine learning, it's our way to connect to infrastructure, right? DVC can manage data pipelines and models, but how to do the training, how to incorporate this with, how to share this result with other team members. So this is why CI/CD become a big part of our ecosystem of the project. David was driving this initiative with CI/CD. And today he will show you how CI/CD for machine learning works, how CML project works.
Great.
Thank you.
Awesome. Thanks, Dmitry. You ready, Sagat? He's going to show us pipelines. Let's do it.
So hi, everyone. We have been working on improving pipelines feature in DVC for quite a while now. So our objective with the pipelines in the DVC is to kind of keep it lightweight, yet powerful. So with that, we introduced DVC YAML file format in 1.0, which made it easier to like make it read, write, and define stages in pipelines, and that too in a single file. So with parameterization in 2.0, we are trying to reduce duplications between params, your configs, and between stage definitions in the pipeline. So I guess before jumping into the demo, let me go through the setup that I have here in front of my screen. So what we are trying to do here is building a binary classifier based on this data set. So what we are trying to do here, we have two stages, prepare and train. In prepare, we take the data set and try to like keep generate the partition data set for that specific digit that we specify here as norm1 with the flag, and it generates this output, which we then use in the training phase. We specify that as dataset flag, and it trains the model, evaluates it, and generates a matrix file which we specified using this flag, and it has some of the configs, and it generates that matrix for us. Not only that, I also have params that is used by those scripts here to compute things. Okay, so that's the setup that we have right now, and let's start with the DVC X-run. Okay, so we DVC ran both of those stages in the pipelines. It threw a warning here, but let's ignore that for now. We'll come to it later. It ran prepare and then the train. So it worked now. Okay, so now let's come to the parameterization introduction of it. So the parameterization, like I said before, we want to help users by trying to reduce duplications in their DVC YAML and in their repo as well. If you take a look into this DVC YAML file, you will notice that we have some of the flags, I guess you could call it config, for your script that you specify as this thing. We also have some parameters in the params YAML file, and we also have some duplications. If you look into it here, we have some common file names and configs spread around between the stages. This is however a kind of a two-way pipeline setup that we have, but in real ones you might have a multiple stages sharing these same configurations or like definitions between the stages. Let me introduce the parameterization syntax for it. With the with parameterization, what we can do is have all of these kind of configs in the params YAML file, and we can just reference them in our DVC YAML file. So let me start with the syntax here. So the syntax for the parameterization is similar to the environment variable that we have in the bash. So it's $braces, and you can have some variable or values specified inside of it. So let's start small with max iter here. I have already put that into the params YAML file, so we can just try to reference it and see what happens. So $braces and then the actual variable names. So this should be it. So let's try to run that again and see what happens. Okay, so DVC is saying that both of those stages didn't change at all. So even though we have changed it to parameterization, I mean, fundamentally nothing has changed, right? It's still the same value. So DVC didn't run that at all. So now it's when DVC runs it, it tries to substitute that value during the runtime, and we'll run those values. Similarly, we have, like I said, we have some of the other things that are duplicated between these stages. So what we can do here is extend that same concept and move these things back to the params YAML that we have. So let's start. Let's start with the model section. I'm trying to kind of keep it generic so that we can have more models later in the demo. So I'm starting with the model section, but you could just start with the one. And let's have that as a data set, and let's have the metrics as metrics 1 YAML, and num being the one, because it's, I guess that's what defines that section. And what we can do here now is try to substitute all of these usages that we have here with the new parameterization syntax. So let's start with the one here. So $braces again, and what we want to get the value is of this num. So we have to go through this models dictionary that we have. So models.1.num. So you can access the nested dictionaries using the dot notation here, and in this way you can get the value of the num directly. So same thing here as well. What we can do here is change all of those to models.1 data set, right? And same thing here as well. Models1 metrics, and similarly here as well. So that's now we don't have that much duplication. Even though we have it kind of references the thing that we have in the params YAML file. So even if we change this value to different thing, our DVC YAML definition in the complete pipeline will still become consistent. But let's roll back now and let's try to run it again. Okay, so same thing happened, right? The stages didn't change at all, because even though we have put that value into the param SAML, they are still this same similar, I guess, equivalent definition as before. So we can consider this as working. Okay, so that's about parameterization that we have. We also, so we have dot notation, and we also can access the value of a list using this kind of index notation. So just similar to what we have in Python, but we are not using it right now. Okay, so let's move into a feature, new feature, kind of adjacent to the parameterization, called for each, and see what it tries to solve. So for that, let's imagine that we want to prepare a set of another data set for a different digit. So what do we do in the 1.0 was we would copy that and try to change what we need to change, right? So we would probably make this into 2 and change this into a different data set. So even though they have quite a lot of similarity, we need to copy things. With for each, I guess let's run this stage now, and let's move on to the for each do later on. So we can create this for the second digit, but we have an issue here that we have no value for the no config for the second digit. So what we can do is we can copy this again. So this demo is all about copying things. So we copy things again here and make it for the 2. So now we have a 2 models.2 section. So we can use the reference to the models.2 now. So now prepare2 will use this config, and DVC will substitute that when it runs. Same concept with the parameterization that we had earlier. So we can run it now, and so it ran that prepare2 stage and was done. Okay, so now let's, I guess, extend this same thing to a different digit, let's say for the 3. So what we would need to do in the 1.0 pipelines was copy things, right? So we would do 3 and 4 and so on. So with 2.0 for each do feature in DVC, what we can do is try to define these kind of same but different stages in a single section with for each do. So the for each do syntax is this, and they kind of come in pairs. So for each kind of takes an iterable, so it can be a list, a dictionary, or it could use parameterization to reference something that's in the param SAML file, either be a dictionary or a list. And do kind of encapsulates the user stage definition. So it can have params, command, outputs, defs, whatever that we had earlier inside of it. So we can just indent it. So what we want to iterate through is this models config, right? So we can use parameterization and reference them from param SAML file with this syntax. So with this, we can iterate through this complete stage definition twice, because we have 2 things at here. So I guess let me try to draw some parallel with this for each feature that we have and what we have in Python. So how you would iterate through a dictionary in the Python was this way, right? So you would get key and item in each iteration. So similarly, DVC tries when it iterates through, you get value, key, and item that you can access through parameterization. So when we are iterating through these models, what happens is we get key being 1, and this models.1 as part of an item that we can access through parameterization at the first iteration. So on the second iteration, we get this 2 and as a key and this as an item. and that way it iterates through. So what happens here is that we get the item here that we can access. So we can take the help of that to replace this and iterate through prepare twice. So on first iteration we get models 1, and on second we get models 2. So what we can do is we can just replace this with item, so it will be same thing as models 1 that we had earlier, and same thing here as well. So now we are iterating through two of those um, values, so we don't need these two at all, because this will have both of those definition, and since it's for two stages, we don't need that identifier as well. So that should be it now, and let's try to run it. Okay, so it ran that again and it was already complete. So it ran two stages, prepare at 2 and prepare at 1. So it ran two of the stages. The order in which it goes is determined by the order of the DAG, but so it's not the same as what we have defined here, but it's based on the DAG. And it ran two of the stages, prepare at 2 and prepare at 1. So you can see that the naming is quite different from what we used to have for the for each stages. So it kind of appends what we have in the key at the end of these stage names. So prepare at 1, and then it goes with the different name to on each iteration. So that's how for each do works. So we can do we can also extend this same thing for the train model here, and we can we can produce two models with the help of parameterization. So same thing do, and what do we get do encapsulate that is test definition, and what we get here is models 1 is kind of equivalent to item in first iteration, and models 2 in the second iteration, which is what we needed, right? So we can just replace all of those with the item, and it will now use this values for the first iteration and the second one with these values. Also, let's remove that because it's not required now, and let's try to run it. Okay, so prepare at 1 and 2 didn't change because we already had run it before, and now we have train at 2, and we should have train 1 as well, because but it's cached because we had already run it. So this should be it. So that's how we have for each do that kind of tries to reduce duplication between pipeline stages. One feature to mention, one nice thing that we get with the use of parameterization in keeping all of these configs in one place is that we can use experiment run set param and affect all of this pipeline with that value. So we are getting a warning here that it's not getting converging because of low iterations. And what we can do is we can just change it to certain value, and it will now run the whole pipeline and even change this parameterized value and definitions. Okay, so it trained that with 1000 value, which it substituted through parameterization, and it worked with the experiment run set param as well. And we can see all of those runs that we had during this demo with the DVC. So we have these nice experiments and all of these values. So there are more features with the regarding parameterization and for each do, like specifying a different file other than params.yaml. You can also have some local variables inside here. You can even have for some locally defined list or a dictionary inside of the for each instead of referencing a different file. But I'm not going to go through that. Please check out the docs, and if you have any questions, feel free to ask.
We have some other questions here. Please feel free. I was going to call on Eleftherios. Are you here? If you want to ask your questions. He says, our team is using mainly the DVC repro command, which will be deprecated in favor of DVC exp run in version 3. Why? For your information, I've already tried DVC exp run, but it's much slower than repro. So that's one of our questions today.
I think I can answer the question. So yeah, we are moving to experiments. It's a bit different way, more flexible way to manage your runs, and we are thinking about removing repro. So it's the repro versus experiments about different flow. I would say very likely we will keep some functionality like repro inside of experiments. So I would not expect it will be deprecated. It will be most likely moved under experiment umbrella somewhere.
I'd also say if you're finding experiments slower than repro, if you could open an issue, that would be great, because that's not expected behavior. They should be functioning very similarly.
Yeah, that's true. Also, it was a good question about docs and how it represented in docs, the pipelines. Saugat, can you show the doc, like DVC doc output? It might be interesting to see.
Sure. Yeah. So it's the parameterization is kind of a factory rather than just simple parameterization. So it kind of builds stages for you. So we have two pipelines here because they are kind of quite separated. But I mean, we just treat the one stance of that for each loop as just a stage. So for each does not, I guess, affect the DAG at all. It just depends on how you are having those files in the dependencies and outputs. So in this one, we have kind of two separate pipelines for each of the digits. So we have two pipelines here.
Yeah, that's cool. In real cases, most likely you will have some initial data set, right? It will look like an actual graph,
Right.
an actual DAG. But yeah,
I've asked a question about pipelines, and was mentioned that I'm more interested not how it would be looking in this particular case, but how it would look if I have two different data sets which are processed by the similar stage. And would it be like the similar, like two parallel pipelines, or just like a tree-like structure in this case?
Yes, I mean, it will be similar to what we have right now, I guess, without for each two. So it does not really affect that. I guess it will be the parallel branches. I guess it depends on what you expect. I mean, we haven't like implemented any special stuff for showing the pipelines if they are part of the for each do, or if they were generated by such method. But yeah, if that's how you would like to see, then yeah, I guess please open an issue, I guess.
Okay, great. We have a question from Eric. Eric, did you want to unmute your mic and ask it?
Yeah. Can you hear me?
Yep.
Okay, cool. Let me just show my face as well. So hello. So I was already using for some experiments the DVC experiment run, where I used the queue and set up the parameter. One of the things that happened was that I made a typo, and then I didn't saw that after the end of the experiment, which ran for 1 week, that parameter wasn't used because it wasn't in the parameters.yaml. So my question is there any plan for checking the parameters are valid in the params.yaml file, so like catching typos and such?
So was the parameter that you entered was not a parameter that was in your params.yaml? Is that the issue?
Yeah. So instead of train.model, I use training.model.
Yeah, that's interesting. Yeah, again, if you could open an issue, that'd be great, because I thought that we had already tried
DVC
to
should
implement
be-
that, but maybe there's something missing.
Yeah, I guess DVC should be kind of checking those values.
Yeah,
Thanks.
so maybe there's just a bug there.
Yeah.
Okay, I'll check and then I'll submit an issue.
Thanks.
Thanks.
Okay, we have one more question from Matthias. What's the idea behind not letting me .git ignore the DVC log file?
I guess, yeah. I guess the decision for that was because experiment kind of uses Git to have those log files and DVC files to track your repo. So it might be kind of tricky, one thing, and might create weird use cases for the experiments. I think the next one was because we wanted to kind of optimize DVC and speed up things. So DVC would not need to like go through ignored files.
Okay, great. Thanks, Saget. All right, we have.
Can I
Okay.
add to that one more question? So isn't that some kind of unexpected behavior if let's say I run my experiment on one machine, and then I maybe change the machine, checking out my Git repository again, and running a DVC repro, which says, okay, my MD5 hashes for the stages are fine. I already run all the stages, but it might be that running experiment on various machines with various setups and various hardware results in different, will bring up different results for my experiments. So that's some kind of an issue. I mean, I could just not push the DVC log file for my experiment and just rerun the experiment on a different machine, but that's counterintuitive to what the expected behavior of the DVC log file is, right?
Yeah, that's a good question. So your concern is if you don't capture environment, right? Different machine might have different environment with a different output, different result, right?
Yes.
Yeah. So in DVC, we decided not to implement it in the DVC level and extract it outside, just because, I mean, otherwise DVC becomes like quite a complicated piece of software. We decided to just split this part from, separate this part from DVC. How to do this? People do this in different ways. One way is to train in the same environment through some Docker containers, for example. Another way is to use a bit different process and use CI/CD, which can capture all the environment. So in this way, you kind of move in this environment management part to some other technology, to Docker or CI/CD. So this is what we recommend today. If you have some ideas how to make it inside DVC, it will be great to discuss. But there is a chance that it will be a bit too complicated to become a part of DVC, because DVC was designed with a very specific goal.
Okay, we have here also Anton Kulaga. He has done he's used DVC in pipelines to do his longevity research, and he was going to share a little bit about that.
Okay, thank you very much for inviting me. Let me share my screen. I am a member of Systems Biology of Aging Group, Biochemistry Institute, Romanian Academy. And so our laboratory mostly does bioinformatic analysis in longevity and also in some other area like autoimmunity. And recently we published a paper where we experimented with DVC usage for machine learning pipelines. So the paper was about feature prediction of longevity related genes. I will just say a few words about the paper and switch to the use case. And everybody knows that different species live different time, and here you see like dependency between mass and longevity. And some species are outliers, that they live way longer than they should be according to other parameters. And some species are extremely long living, like bowhead whales that lives more than 260 years. So the key idea of the research was to compare species of different lifespan, mostly their transcriptomic data, like activities of different genes, and find genes that are the most predictive for high lifespan of long-living variables. So overall, the specifics of the project is, I mean, in bioinformatics, usually you deal with very wide data with small samples numbers. So we had around 400 samples, 408 samples for 5 tissues models. And each sample was around 11,000 genes. And we had to combine a lot of machine learning methods to find anything with such a small but wide data. And here is the pipeline. So we had several components. The DVC part was mostly used for dealing with, for pre-processing the data, and also for light GBM and sharp models, and also for integration of the results. In light GBM plus sharp model, so we had some. In our case, so the data in bioinformatics, usually raw data is quite large. Like you can have, say, 6 to 8 gigabytes per RNA-seq samples. So it's like gene expression. Or if you talk about genomics, it can be like 200 gigabytes per genome. We worked with transcriptomics, but still we use specific workflow engines like Cromwell to process the data and get gene expression. So the part with like raw processing was done with Cromwell. But after that, when we got already gene expression numbers, then I used a mix of, so the code was overall Jupyter notebooks that were run with paper mill tools that runs, that allows running notebooks headless, so like from DVC stages. And then it generated the data. And for light GBM plus sharp, we had 3 stages. So it was like a backward selection where we had results of the first stage was used as input for the second stage, and so on. For other models, unfortunately, I didn't manage to get colleagues who were doing linear models and Bayesian networks to use DVC, so they had separate repositories. But I integrated their data on the third stage, so it's stage outputs and results. So we had ranked list in the end. And I don't want to talk much about results, but it's like a typical example of the output. And in our case, what mattered was not only metrics in terms of numbers, like accuracy or like Huber loss, but also often you look into like sharp charts and see overall picture and read a little bit about the genes and see how biologically pleasable the results are. So in evaluation, also some charts played also role, not only numerics. And in the projects, as I mentioned, so overall, I want to say that the projects in academia are very different from the industry. So we had some rough edges that probably people who are using DVC outside of academia, I mean in the industry, they probably don't have them. So overall in academic and research bioinformatics, usually there are many people, but usually each person, they work on multiple projects. So a project you are involved in is not like your own project. You have like maybe 4 other projects. So you don't have big time to spend on like improving the code quality, learning all the tools and so on. And as we couldn't, usually people just have separate repositories and then they just integrate things together. In the project, one repository with DVC was shared with me and Vlada, and there were 2 others that just computed results separately, and I use their results as external. What also like strikes when you go to academia is that often typical way like in software engineering, like you write good maintainable testable code, often it is not working well because sometimes you have to like deliver results very quickly, and you cut the corner. So you produce some throwaway code, you get results, you give to colleagues, maybe you will have another idea and you will not need to deal with this code, so little incentive to improve. Another thing is that notebooks matter, so it matters a lot. And of course, the last thing is specifics of data sets that are wide but small number of samples. And we use like micromamba/conda to manage dependencies. And we called notebooks from DVC. And we used Google Drive as for DVC remote. And by that time, there were like, it was like early version of DVC. So people hated me because DVC had many bugs, but DVC developers were extremely helpful, that they spent a lot of time helping us fix it. And the main issue, so by that time, we had to make branches to have like metrics. It didn't work. I abandoned this idea because it was too much a headache. Now, of course, you can avoid doing it. You can have multiple runs without branches. With notebooks, the main frustration was that if you have stages that depend on each other and you change the notebook, how can you tell DVC that it should re-render according to notebook changes? And notebook change, it can be code change, but you also have to track that sometimes output changes a bit, but the code is the same. So it was like an unsolved problem, I would say. Downloading large files were extremely confusing for the team because it's very counterintuitive that if you have external source, you import it, that by default, you have to push it to your remote, even though it's external, or you have to do some hacks to actually avoid saving it in a cache. And the other problem was integrating with other tools. So there are workflow tools in bioinformatics, and they do like caching and so on. And maybe what can be useful is a way like to somehow track their input and output in the pipelines, because right now you are in a big struggle. You choose whether you want to use DVC for a part of a pipeline or you use a specific workflow running tool that is more dedicated to running pipelines that can fail, that need Docker and so on. Maybe there are ways to make them friends, I don't know. And the lack of fixed share support is a problem. So for like final results, usually in academia, people publish not in Google Drives like we did for the data, but on a Figshare. And but anyway, it was quite useful experience. Here is the team that did the project, and I am continuing to use DVC in 2 other projects of mine. One on adaptive immune repertoire sequencing, and the other one is an open source project where everybody can analyze his own genome, like sequenced at Dante or any other place with open source tools. And for this, I want like to say thank for your attention, and sorry for taking so much time.
That's okay. It was great to hear about your use case. We really appreciate you sharing today. Thank you so much. But we're gonna next go to David Ortega. He's gonna go do a demo on CML today.
Okay, let me present you what is CML, continuous machine learning, and why we should move our machine learning project into a CI/CD environment. I have here a question before about that, the reproducibility of an experiment, and probably this will throw some enlightenment. But okay, what about CI on common software? What is CI about? And everything, I mean, CI is mostly, hold on, it's about the green light, right? I mean, you set up your software that you have to pass some tests, integration tests, unit tests, I mean, smoke tests, all the tests that you may imagine to have that green light. And of course, we can adapt our machine learning to that strategy, right? We can use Gitflow, for example, just to create our project, our machine learning project, and every single experiment can be a pull request against our master branch. And with that, we can have also the perks of releases, right? We can have, and we can create issues around our machine learning project that is going to come up and during the real life cycle of your model. But for me, one of the most interesting parts of using a CI/CD for machine learning is reproducibility. Because, and this is the key thing, right? I mean, when you set up your CI/CD for a common software project, you are constraining how it should behave and what is the expected output. So we can have also that outcome. But the most important part also, and for me super exciting, is the workflow. The workflow of a CI/CD itself is like a contract. I mean, the strict or the tight that you make that contract, you are going to ensure the reproducibility of your experiment, not only for your peers, which is actually almost automatically, but also for you in the future. I mean, you can actually set up very well your machine learning project in a CI, tighten the version, tighten the machine, the whole environment. And that project for sure is going to work today, and there is no reason that project, that machine learning project, is not going to be reproducible in 10 years from now, right? That's the idea. So for that, CML is creating a series of tools that can be used locally or in the CI, and I want you to present them. Number one, we have TensorBoard Dev, which basically is launching a TensorBoard in background, so your workflow can continue. But at that time you are launching it, it's going to return you the URL of tensorboard.dev, and by that time it's actually tracking your experiment, right? So you can get started and you can use this URL in your report, as we are going to see later on. The second command is CML publish, which allows you to publish any file into our storage. However, it supports also native storage. For example, in GitLab, it's going to use GitLab storage instead of ours, just for privacy reasons. And it's also returning you a URL where the storage is going to live. It supports Markdown or HTML. The next one, and super important, is the CML send comment. Basically, it's going to send a comment to the specific commission and the repo, and you can use also Markdown. And this is going to generate a comment in your pull request, right? A visible comment in your commit. So this is how we establish a very simple way for you to generate reports. The next one is the CML runner. And this is for me the most exciting part ever. I mean, as a personal use case, for example, this is the way I can actually launch GPUs on private networks with no effort, right? I can run it locally, and it's going to expose my GPUs into my GitHub workflow or GitLab workflow, and I can use them and take the most of my machines. As you see, it's very similar to the original ones, but we are always trying to improve simplicity. And what we have improved here is that when you launch it, you just specify the labels and the idle timeout, and this is going automatically to register our runner inside our inside GitLab or GitHub CI. And when it destroyed, you can see here, for example, that the idle timeout was 30 seconds. After the idle timeout is done, and there is no experiment to be run, or there is nothing to be done, the runner is going to automatically destroy itself, also unregistering it from the CI. However, this is not the most exciting. Despite it is super exciting for me, this is not the most exciting one. The most exciting one is that the CML runner actually is able to launch this in cloud resources without almost no effort. For that, we use a Terraform provider, iterative Terraform provider. It's a Terraform provider that we are making that is abstracting in a very simple way the major cloud vendors outside, specifically all of them that supports GPU, which is fundamentally important in CI and in machine learning. And here you can see that we are going to launch an instance in AWS, US West. It's going to be a small for testing purposes, and it's going to use our Terraform provider, and it's going to launch the machine automatically. It may be, it's very simple to be used, and we are going to see then how it's going to be used in a workflow, in a CI workflow. Of course, this is the machine prepare is going to launch the runner. The runner is going to register itself alone again in our CI, and then on its done, it's going to unregister. But the most important part also is that it's going to destroy itself, the machine. So we don't have to take care of these ephemeral machines anymore. So we can launch the GPU as fast as we need it, or at the time we need them. And once the training is done and all the experiments are meant to be done, the idle time is gonna come up, and the resources are going to be destroyed. So let's review how we can do a complex case scenario that you might find in our cml.dev page. We have 5 experiments, super easy to follow from beginning to the most complex scenario. And what we are going to build here is a very simple pipeline of 2 steps. The first step is going to deploy the runner with a GPU that we may not have in our houses or locally, or we need to rent them. And then we are going to run the experiment. So in our YAML file, as we were saying before, we are going to generate the job that is the deploy runner. So we can say, we say that CML runner, cloud AWS region, the type of machine that we are going to launch, the labels, and this is step one. Super simple, very straightforward, just only one line command, right? Very easy. And the second one is the train, what it happens, everything. So I'm saying that I'm going to use here container. This is a very, as we were speaking before, for reproducibility, the tighter you make your environment, the most chance your experiment is going to be reproducible always, right? So if you fix your version, every single version that you have, or is perfect. So we may have our image, you can use your image. We specify that we are going to use all the GPUs available in the machine, and then we are going to do the workflow, right? We are going to install ImageMagick, the requirements of the project, and then we are fetching the data, and then we are creating our report. Basically, we are calculating the metrics and the differences and some images, and then that's going to be sent with CML send command to CML, to the CI as a beautiful report. Super simple, super straightforward, right? So at the very end, what you have here is a reproducible experiment. Anyone can clone your repo, or you can give access to your repo, any peer that you may have, and just only creating a branch or just only clicking the button, redo, rerun the CI is going to have consistent output to the experiment, and it's going to generate a very similar report. So it's just a matter of just changing your parameters and that you may need, create your push, and everything is meant to be as perfect or equally the same as it was. So this is a very simple, straightforward representation of CML. Hopefully you have some questions. This has been a little bit fast, but I'm here just to answer any question that you may arise. And thank you very much for viewing, and see you around.
We have a question from Miha Janko. Does the CML runner implement caching mechanisms like the GitHub workflows runner?
It's a very good question, actually. This is definitely in our pipelines. It's not going to be using caching mechanism. We have opted to create shareable and reusable disk is something that we are right now working on. But of course, here what you should be using, and CML is actually working to be super tightly integrated, is DVC. DVC could be potentially the substitute to anything else, right? You can use DVC to run your experiments. Actually, in the example that we have seen, we are using DVC repro. So DVC is the one in charge of running the repro. And this is very interesting and very important in the CI, because DVC is going to check out if nothing has to be done. If nothing has to be done, the CI is merely like an empty run, right? Everything is in handle of DVC. So I would recommend you to use DVC for these use cases. And of course, we are working for making reusable and shareable, especially shareable hard disks, because I think that there are so many huge data sets outside that should be shared between machines. So there is no need to download like a huge amount of data.
Great. We have another question from Miha also about, has anyone, and Miha, if you can unmute your microphone and ask the question if you want.
Hi, hopefully you guys can hear me.
Yep.
Yeah, so I'm trying to standardize model versioning. I want to use like a GitOps approach and using Git as a single source of truth. for deploying models. And for that end, I was thinking about writing specifications like model dependencies and model parameter values for deployment in a YAML file. And I was wondering if anyone has come across a good standard for this. Like I can just come up with a YAML schema right now, but I want to use something which was put more thought into. Anyone with this experience?
Yeah, I can share how we can help with DVC on this. DVC codifies all your data models and the metrics, right? In this way, if model was produced with DVC, you will have this YAML file with the reference to the actual data set, right? Which might be like on S3 or some NFS storage inside. So DVC gives you this this model. And also you can attach metrics through DVC pipelines. So you can have not only models, but also correspondent metrics. And we have a set of APIs how to work with the models through command line, when you can say DVC get from this repository this particular model, and maybe with this particular revision. For example, give me model not from master, but from version prod, or from some feature branch or some particular checksum. This one approach. The second approach, we have a library. In the library, you can do the same. From the Python, you can say, there is a repository in a GitHub or GitLab, and I need this revision of this particular file. So you will get the file, and it provides you Git-like API to your models. In a similar way, you can access the metrics if metrics are specified in the pipeline.
Can I add a follow-up here? So can you perhaps use like writing these parameters like params YAML without actually running DVC run exp and these kind of tools, where you could just use a DVC command just to write down the parameters, regardless of whether you use the pipelines or not?
Yeah, parameters usually they're committed together with model. If you have like some commit, then what it means that the model is kind of quoted committed in the repository, at least the pointer to the model, and the parameters file should live somewhere close to it, right? So your commit become a pointer to the parameters and as well as models. So in this way, you have this perfect match, and it gives you for this, I mean, lineage, right, between the parameters and the final model. You might use pipelines, you might not, but this connection, Git makes this very clear.
I know Mert had a question. Mert, do you want to ask your question?
Yeah. So I just wondering about, is this process about Docker or container things and DevOps? I mean DevOps things.
Yes.
Yes.
Yes. Actually, the original approach of CML and the one that we still follow up in GitLab is using a Docker container.
Okay.
Basically, CML is a Docker container that you run your workflow inside that. GitLab also supports Docker in Docker, so it is very simple. And so the idea is as we show in the workflow, ideally you should create your own Docker container where you set up your a specific version of your stack, right? If you are using R or Python, PyTorch, or whatever it is, you create your own environment and you are going to use that in the workflow for seeking for that reproducibility. Our image, our CML image, that is still, we still push toward that in GitLab, also come with the perks of CUDA. I mean, you have everything installed just to take the most of the GPUs out of the box. And when we deploy the CML machine in cloud, that's prepared. I mean, that's preparing the machine, installing all the GPU drivers, NVIDIA, Docker NVIDIA also, for you to be able to use your images and access the GPUs inside. So yeah, I will say that CML is, as many of the CIs out there, is looking tighter for using Docker. I think that Docker is a great idea to containerize and make the whole environment very easy to be reproducible. And in the next release, right now, CML Cloud is supporting AWS and Azure, but we are releasing very soon Kubernetes also. So
Yeah.
that's gonna be the third vendor.
I actually started the MLOps tutorial and learning CML, but it's hard to me because I am first grade student at the university, and DevOps and backend concept and CI/CD continuous integration concept is so hard for me. I don't know how to handle this situation.
Yeah, you can ask more questions on the channels, right?
Yeah.
To learn this. And I believe most of the questions will be related to CML in general, not to in the CI/CD in general, not even CML. I can add about Docker container. David mentioned that we are providing this as a kind of default mode of using CML, right, through Docker container. But actually, you can install it as a library. So CML is just a JavaScript library you can include in your own container. It's very straightforward to do. And Vera is online, and she was the first person who asked for this feature when CML was released, like literally like next day after the release. Like why? Like she was saying like why you are pushing to Docker too hard, something like this. It was on Dev 2 as far as I remember was your question. And now, yeah, we decouple it, and actually you can use it separately if you prefer. But Docker is still a best practice. So it's totally up to you. You are muted.
Yeah, I have written on the chat. I have written them on the chat, but if I can spin up a cluster of GPUs and how I will divide the data, I come from a Dask background, so I'm used to be able to interact a lot with my workers. And also I'm stuck in CUDA 10.2 project. So I know that I need the virtual machine to have a specific driver so my Docker can be run on it. DVC, how I deal with this in DVC?
Yeah, okay. So actually, unfortunately, we are some kind of stuck also with a CUDA version. We are not supporting the latest one. And there is a project actually that we are doing to manage labeling in our images, so you can actually specify the specific version of CUDA that you may need, just in case you don't want to install it. As I say, or as Dimitri said, CML is a library per se, so you can install it in your workflow. And the ideally scenario is that you just create your container, installing all the things that you may need, and that's going to be used in the workflow. However, say that, actually the interesting part is that, and we never had done such advanced scenario, and you are giving me a great idea. But in reality, CML supports multiple machines working together. I mean, because what is behind is our Terraform provider. And actually CML can read a Terraform file. And if you specify multiple nodes, multiple runners, they are going to come up together. Say that, there is fundamentally right now an issue that we are also working on that because the CML runner might be running in a very simple scenario, like very simple network, launching, spinning off. That will cover mostly all the case scenario. But for example, for distributed training, or that you may use GPUs in parallel, there is a missing key thing that we are working on, that is to be able to create a much more complex network for your runners to be able to communicate, right? Fundamentally as a software level, which is, I don't know, which software do you use for training, just if I ask? I mean, oh, how did you set up that?
Ira?
I'm most on the PyTorch side.
Okay.
But I'm working on GCP, so I really love them GCP cluster functionality of task, which allow me to deploy through Python code, like new cluster object, this specs, and it's done. And I understand that Underground that has this, it's not Terraform, Kubernetes, but I don't see it. It's transparent for me. But we have a networking group exclusively for that, workers and schedulers and blah.
Yeah, here, that's the thing, right? I mean, we have to distinguish between when we launch the runner, and the runner is going to join our CI, and then we need to somehow communicate them on a software level, right? So that's something that we are working on right now, as we say, to be able to create much more complex networks. And so right now is not available yet. However, with the Terraform provider, you should be able to launch multiple instances, and we are looking into that and to solve that problem, actually.
And so thank you all for being here today. It was great. A lot of really great questions. Great. Thank you to our team for doing a great job explaining everything and answering the questions. And we'll see you next month. So have a great week.
Thank you. And see you next month.